Where did the integral sign go? Where did this go? Right, it went away, right? Because in the process of taking the antiderivative, it goes away, right? I just need you to understand that in the process of taking the antiderivative, this piece also just goes away. Now, you need it there because it's what helps you make the substitution, right? And make all this work. But at the end of the day, when you do this integration step, it vanishes. Now, if you need it to become something just for that peace of mind, just say it turns into the plus c. It's technically not right. But if you need to know, if you need to remember the plus c, then just be like, that's where it comes from the du, okay? But it really does go away. It's like in the actual operation of taking the antiderivative, these two things go away and you just get the antiderivative over there.
Right now, in the last problem, I started tripping. I was like,
Yeah. Yeah, it doesn't go away. Well, yeah, it's like this. I'll give you a more basic example. When we say the antiderivative of this should be sine x plus c, right? Agreed? Now watch this. If I take the derivative of sine x, I should get that, right? Okay, derivative of sine x is cosine x, right? Times the derivative of what's in here, which you would say is 1, right? I agree with you. It's like dx over dx, isn't it? It's like dx over dx. You can kind of look at this du and look at this dx as this piece right here. It's really a 1, but we put it there so that we have a clear indication of what the variable is in the problem. All right? Does that help?
Yeah.
Okay. All right. So it comes from the chain rule. I'll give you another way to explain it. How about this? If I asked you to take derivative of sine, then you would say it's cosine of u, right, times the derivative of what's inside. Agreed? Okay, now if I put an integral here, then the antiderivative of this is just going to be sine, right? What happened to the u prime? You see? Like the u prime is here, right? This is like the du. Do you understand that? Yeah. This is like the du. So when you go backwards, it doesn't need to go anywhere because it came from the chain rule anyway. Does that make sense?
Yeah.
Okay. How about this one? All right, I'm using thetas instead of x's. You comfortable with that? That's sine to the 5th power of theta times cosine theta d theta. Now you don't need to write this next step, but I just want to make sure we're very clear on what the 5th power here really means. That's really what that means, right? The 5th power means you find sine of theta first, then you raise it to the 5th power. You're not raising theta to the 5th power. All right, this one is not necessarily any more complicated than anything we've done. It's just there's something kind of interesting in this one. So anybody want to step up and take a swing at this one? U is going to be what? Sine theta. And that's because you see its derivative? Yes. Cosine theta, d theta. Okay? And I can just rewrite the problem. This is integral what? U to the 5th. Cosine theta d theta is du. And that'll just be power rule. 1/6 u to the 6th plus c. And what was u? Sine. So this will be 1/6 sine to the 6th theta. I'm going to go back to the other notation, plus c. And that is correct. I mean, that is the correct way to do it. Now, why did I show this to you? Because somebody else steps up and says, let's go with cosine theta. Well, what's the derivative of that? Negative sine theta? Well, I have a sine theta in here, don't I? I'm off by a sine, but that's okay. But there's a bigger problem. It's inside of something, right? It's trapped inside of something. It is inside the fifth power. And that's why that's the incorrect substitution. Does that make sense? So this would not be the way to go, all right?
Wouldn't you be able to algebraically still get the answer?
Could you still do it with that substitution? Like if I forced us to try it?
But if it's, you could still maybe pull out the negative or something, and still get the same answer at the end. You just
That's one of the rules that he gave us right in the sheet. If it's trapped,
Yeah, if your du here, negative sine theta, d theta, if this is trapped somewhere, then this is not going to work easily. Your question is, can you still do it, right?
couldn't you just pull out the negative outside that integral?
Okay, so let me do that. I'm going to pull the negative out. But what are you going to do with this? Because you need this over here. So you could do this. You could do this. You could rewrite this integral cosine theta. That's my u. I could write it sine to the 4th theta times sine theta d theta. Isn't that the same as sine to the 5th? Right? And so now I do have sine theta d theta, don't I? Yes? Okay, well, let's see. Again, you ask, I will try and deliver. Do you all agree with that, what I've done? Okay, so I can rewrite this piece as what? Negative du. I can rewrite this piece as u, right? And this would be, u. And this would become, right? I fix it. See if you can follow me. Look, what I'm doing right now, we are going to do later. Remember I said there was 5 techniques? One of them was trig integrals. This is exactly what we'll do with the trig integral, but we'll have to do this. Like, obviously this problem worked best this way, right? We were right there, we got it. This way is not working, like it doesn't seem to be nice, but I'm gonna make it work. All right, so look at this. This is negative du, this is u. This we were like, and now I'm gonna use a Pythagorean identity. Sine squared is 1 minus cosine squared, right? Squared. That's negative du. That's u. This is 1 minus u squared squared. Wait, hold on. I'm going to go ahead and rewrite everything in terms of u now. U, 1 minus u squared squared, negative du, negative du. Yes? Now, you have to expand this. 1 minus u squared times 1 minus u squared, and then multiply through by a u. So you'll have the negative out there. When I expand that, I'm going to get u minus, 2u cubed plus u to the 5th. So I FOILed this out, okay, and then I distributed a u through. You follow me? And then du. And now I can do power rule on each one. Right? I'm going to stop here. Better choice, right? But you can see that with this problem, I could still do it. It's still possible. Now, I have some bad news for you, though. If you were to take all functions that exist out there in the world, every function possible, and you throw them into a big bucket, all right? And you close your eyes, and you reach into the bucket, and you grab a function, the probability that you can solve it using a technique of integration from this class, the probability is 0. There is 0 probability you can do it. In other words, when we're doing antiderivatives like this, we have to make these problems very special so that they work. Because in general, it's difficult to find antiderivatives like this. In Chapter 8, we realize we will learn that, well, there's a guy named Taylor who figured, well, what's the use of this if we can't do a bunch of them for like functions that exist in the real world? And he came up with what are called Taylor series, which allows us to actually find antiderivatives of any function. All right? But you have to throw the techniques out the window. You have to do something else. Fortunately for us, though, in a lot of physics applications and real-world applications, there are a lot of times functions that come up that we can find antiderivatives of. All right, we're ready for another example. I just want you to look at that real quick and tell me how you would go about doing that one. You would do a u substitution? And what would u be? X squared plus 1? Because the derivative of it is what? 2x, and you almost have that, right? And that would work? Agreed? Yeah. I like that. Would it matter if I change this up here to like to the 30th power? Would that change anything as far as your approach? No, because you would still have u, right? The derivative of it is still there. So it would wind up being like an integral with like u to the 30th, which you can still do, right? So that's not too intimidating, I hope. But what if I do this and I take that squared out? Oh, wait, hold on. Let me do this. Let me go back here to the first one I put up here. Let me put them all up here so we can see them. I want us to compare all these.
Did we say that our x squared plus 1 is our u?
Say what?
Did we say x squared plus 1 is our u?
That's what was suggested. On this problem, make x squared plus 1 our u. Yeah. And then let's just make sure everyone's together here. Is everybody comfortable with the idea that the u would be x squared plus 1? Anyone uncomfortable? Sure? Okay. What I was going to say is, yes, that would work, but why not just do this? And then just use a power rule. Could you do that? Yeah, you get an answer. It would look different, but it would be the same answer. So algebraically, it would look different, but you know, if you could make one of them look like the other somehow. So this would be valid? Yes? Okay. This one, I would use the u substitution. Why? You can't multiply that through because the 30th power has to happen first. So this you have to do by u substitution. U is x squared plus 1. What about that one? That's the one I'm interested in. These are two.
So why can't you just still do the power first? Just do the power first.
What do you mean?
I mean, unless in the second one,
Uh-huh.
well, can't you just first just put the power in the parentheses, yes, and then,
You have to multiply this times itself 30 times.
I mean, you just multiply, you did x,
You have to do this times that times that times that 30 times, right?
Can you just put the 30 like inside? I forgot how we can do it.
I'm not sure what you...
Oh, I think I know what you're talking about. You're talking about like, I don't know, it's like adding or multiplying like exponents.
Yes, exactly.
I don't think you can do that because how you said, you're not talking just about the x squared and the 30. You have to do it like all of them 30 times. Like when you're doing the like Mexican algebra, when you, I don't even remember.
Let me help. When I was a student, I had a lot of problems with these rules of exponents and when you can and can't do things. So what I did that helped me, and it may not help you, all right, is I just would try and give myself an example. I think what you're trying to do is you're saying, can you just apply the 30 power to here and the 30 power to here?
Wouldn't it be x to the 60th power?
Plus 1?
Plus 1 to the 30th, which would be 1.
Okay, so if you did that, what you're doing is you're taking this and you're raising it to the 30th and this to the 30th, right? I'm saying challenge yourself to ask whether or not that's legal, okay? So here's an example, all right? I have two things added together. Can I just square each one and add? So let's try it. What would happen if I square the 3? 9 plus square the 4. What do I get? 16. This is 25? Yeah, 25. But what's 3 plus 4? 7 squared is 49. So which one's right? 7 squared, 49 is right. You are not allowed to apply power. So in other words, what I'm saying is this. If you have x plus y to the n, this is not equal to x to the n plus y to the n. That is not correct. If it was, then yes, that's how I would deal with that.
Only if it's a product, not an addition.
That's right. If it's a product, yes. If that's multiplication, then that's multiplication. And then yes, indeed, you're in business.
You can distribute only products.
And that's kind of amazing because look, if I change that to minus or multiplication, then this becomes multiplication, right? And that's 90 plus 45. I think that's 135. No, 144. That's 144. But then, no, that's not. Hold on. Yeah, it's 144, right? 9 times this is 90 plus 54 is 144. 3 times 4 is 12, squared is 144. So see, it works with multiplication. Okay, sorry. All right, back to this. All right, so for this one, we would want u substitution. U would be x squared plus 1. This is the one that I'm most interested in. Now, this x plus 1 to the 30th. See, you no longer have u du, right? You don't have that anymore? You can't let the x plus 1 be u because the derivative of it is not there anymore, yes? I mean, it is, there's a 1, but it didn't work out as nice as the other one was going to work out, right? And you sure as heck don't want to expand that, right? You don't want to do that, x plus 1 30 times. Could you? Could I send you home with that and ask you to come back on next week? How about, let's do that. How about for the weekend, you know what, let's make it 300, okay? And just for the weekend, just go and expand that binomial out. All right, I'll let you go early today. No, there's no way we would want to do that, right? No way at all. And if you were that sick, I would just keep adding zeros until you stopped, right? Okay, so it does not appear that we have a substitution that's going to work here. But you have to again, step up to the plate and do something. So this is the first example that I'm going to show you where you're going to make a substitution that doesn't seem like it's going to do anything, and it's actually going to do it, all right? So here it is. X plus 1. Now, does that seem like if you had to pick something, you know, like I was going to say holding a gun to your head, but then people are going to freak out on that. It's 2018, you can't even mess around. So let's say I'm threatening you to pick a U. You have to. Does x plus 1 seem reasonable that you would pick it? Yes.
Did you say that the x plus 1 will be trapped because of the 30?
Do what?
Like the x plus 1 will be kind of trapped?
But it's not.
It's the derivative that can't be trapped, right? The U can be doing whatever it wants. It's the derivative that can't be stuck inside something, all right? So the derivative of this is just 1 dx, right? All right, so I've got this. That dx I'm good with. That's going to be u. I've got to replace the x. Okay, so I can do this, right? I can solve that for x. U minus 1 is x. But this just doesn't seem like it should really gain anything because this derivative doesn't seem like we would gain anything. But just watch what happens. Okay, I'm rewriting this. What's x? U minus 1 in parentheses. And then what's x plus 1? That's u, but u to the what? 30th, and then dx is du. So have I done anything that's going to help, or is this just still crap? Yes, you see, here we would have to expand a binomial 30 times, right? It's a monomial here. It's a single term. I can now just distribute that through the parentheses. Right? And I just get, what, u to the 31st power plus, or minus u to the 30th power du. So somehow, by making this substitution, which did not seem like it was going to gain much, it helped us avoid ever having to expand the binomial. And so what we get now is just power rule. This is 1 over 32 u to the 32 minus 1 over 31 u to the 31 plus c. And what was u? X plus 1? There it is. You have to take a swing. I'm not convinced that's the antiderivative. I'm not convinced. I want to check it. All right, so let's take the derivative of this. If we take derivative, we have two separate things, right? So first, the 32 is going to pop out and go away, right? So I'm going to have x plus 1 to what power? 31 power. Minus, now this one, the 31 pops out. It's gone. I have x plus 1 to the 30th. That doesn't look like this. It doesn't look like that. Unless you realize that they both have an x plus 1 to the 30th power in them, right? And so you can factor out an x plus 1 to the 30th power out of both of them. And what would be left if I pulled out 30 of these x plus 1s? I would be left with one of them, right? X plus 1. And then minus, if I pulled out all 30 of these, then what am I left with? A 1, and then these ones cancel, and you get x times x plus 1 to the 30th. Why what? Why is it so beautiful? Oh. Let me pass around the sign-in sheet. We're not leaving yet. There's no such thing as doing too many of these problems. Here you go.
I think this is the best way of learning, just like keep doing examples.
Yeah?
Class, and that's it. And then we just study a problem. That's it.
You've got to, for every one problem that I do here, you should be doing at least, 6 for every one I do here, really at home, right? That's how much practice you need with this. Oh, yeah, I like this one. I can do some sort of Are you all starting to see what I mean by there's just something inherently different about Cal 2 and going backwards? Yeah. That it's not like mechanical like Cal 1. It's not product rule, quotient rule, chain rule, where I just provide you with formula, then you just operate the machine. Like you actually have to try things, try something else, see some algebra. I know that you get in trouble for being on your phone, but I'm letting you think.
natural log of pi.
Natural log of, for your u? If you're going to choose a u, then you need to see the u in there. Like, I wouldn't choose u as natural log because there is no natural log in there. Right?
Also pi over x.
So why would you pick pi over x?
Wait,
Because that there's something. Side.
I was looking at a tangent of pi over x.
So, okay, so if this doesn't work, tangent to pi over x maybe next?
Yeah.
I'm not looking at the whole thing yet, but
What's the derivative of that? That's the antiderivative, be careful. This is really pi, which is a constant, right? X to the negative 1. That's what that is. What's the derivative of that? Negative pi. Then subtract 1 from that, it becomes negative 2, which gives you an x squared on the bottom. An x squared on the bottom. I have an x squared on the bottom. Right? I just don't have a negative pi. That's okay. I can get rid of the negative pi. How do I get rid of the negative pi here? Divide by negative pi. So how about this? It becomes 1 over negative pi. This is looking promising, isn't it? Is that not looking promising? Is that rain? No. Sounds like someone flushed the toilet on the 4th floor. Oh, wait, I didn't want to do that. Okay, what I wanted to do was secant of pi over x tangent of pi over x times 1 over x squared dx. All I'm doing is rewriting the problem, but I'm peeling that x squared off to the side so that it becomes very visible to you that that's going to be our du-ish looking thing here, all right? So there's our du thing. And then pi over x, that's going to be replaced with u, right?
Then you can say that x squared is equal to dx over du over negative 2. I mean negative pi. X squared equals dx.
This side I just divided both sides by negative pi, right? And that left a 1 up here, 1 over x squared dx. That's exactly what I have here. Like, these match up perfectly.
We still need to substitute the negative 2. I mean the x squared on the other side, right?
No, this is already, I pulled this over here, see? See, it's no longer underneath here. It's just slid over to the side.
Oh.
So this becomes secant what? Secant u, tangent u, and then this whole thing right here gets replaced with this right here, right? And I'll pull that I'm going to write it like this, negative 1 over pi du, like that. And now I need to know what the antiderivative of secant u tangent u is. Uh-oh. It's just secant u. So you have to recognize this as one that we saw in Cal 1. The derivative of secant x is secant x tangent x. So the antiderivative of it is just secant. So negative 1 over pi, and then I have secant u plus a constant, and then I replace u with pi over x plus c. There it is. And we could check it real quick. If we ignore this, what's the derivative of secant of something? Secant of it, tangent of it, right? There it is. Times the derivative of what's inside. When you take derivative of what's inside, you get that right there, right? And if I multiply that by negative 1 over pi, the negative pi's cancel, and I just have 1 over x squared, which gives you that. So it works. All right, I've got about 9 minutes, so I want to show you something. There comes a point where there are certain integrals that keep just popping up over and over and over later on. They just keep appearing. And we want to become very fast with these without actually having to do the U substitution. So let me show you an example. All right, you see that one? I'm just going to show this to you real quick. I could do a U substitution of 4x right now. The derivative of that is just 4 dx. So this right here is u. I need dx, so I divide both sides by 4. And I get dx is going to be 1/4 du. This integral then becomes 1/4 integral cosine of u du. And that's just 1/4 sine u plus c, which is 1/4 sine of 4x plus c. Right? Okay, I did that kind of quick. So I'm wondering if from that you can tell me what the antiderivative of cosine of a times x would be, where a is just some constant. So a could be 4, a could be 5, a could be -2. Like, what's going to wind up happening when I take the antiderivative of this? What am I going to have to do? I'm going to have 1 over that number out front, right? So this is going to become like 1 over a sine of ax plus c. Does that make sense? Now, don't quite box that as a formula yet. I want to add one more thing to it. What if I had put in this formula plus 1? Would that have made any difference in my, I mean, this would be plus 1, but would everything else have worked the same? And then I would have had, here plus 1, but I'd still have 1/4 out there, right? When you take derivative, it's just 0. So maybe we can extend this formula a little bit, okay? Maybe we can do this. So let's say that we have cosine, and in here is linear. Now, linear means, like, remember y equals mx plus b? Like, this is kind of like, mx plus b. This is a number in front of x plus a number by itself. That's a linear expression. If we're trying to find the antiderivative of cosine of a linear expression, it should just be 1 over a sine of that linear expression plus c. That you can box. That is something you should memorize. And don't look at it as a formula as much as, like what's happening. A couple of quick examples with this. What would the antiderivative of that be? 1 over pi sine of pi x plus 1 plus c, right? The whole reason it's that is because this is linear in here, right? So this would be 1 over pi sine of pi x plus 1 plus c. All right, let me give you another one. Cosine of 1 minus 5x dx. What is that? 1 over 5? 1 over... Okay, so I tried tricking you intentionally here. This is the same as negative 5x plus 1, isn't it? So a is negative 5. And the formula is 1 over a. So it's going to be 1 over negative 5. Sine of, I guess, 1 minus 5x plus c. What you want to focus your attention on is that if you have a linear expression sitting in front of cosine, sitting inside of cosine, the antiderivative is just sine of that same thing, but scale by 1 over a. Yes?
Does it have to be cosine or a?
Well, that would be my next question. What do you think the formula would be if we had antiderivative of sine of ax plus b? You still think we're going to have a 1 over a in there? Yes, but there's an issue that when we take the antiderivative of sine, we get negative cosine. So instead of having 1 over a, it's going to be negative 1 over a, and then cosine of ax plus b plus c. So these are the two formulas so far. And again, don't think of it so much as a formula as trying to understand that if you let this be u, right? If you let this be u, what's the derivative? A, right? And you have to scale that out. You have to get rid of the a, so you have to do 1 over a on the other side of the du. Same thing with this. If I do a u substitution here, the derivative is a, so I need to scale it. All right. I need to point out one thing. As you're doing your homework, what you're going to see on these problems when you do your homework, I'll give you an example here. There's a problem here that is as follows. There we go. All right, so that's the cube root of this, right? Now, you see those numbers right here? Yeah. Ignore them for right now. All right? Just completely ignore them. Just go try and find the antiderivative of this. Now, be careful, because if you check your answer in the back of the book, you're not going to get the right answer, because this actually does mean something. We're just not going to deal with it. So if you want to check your answer, you would need to check my video, and that video would have the antiderivative in there. All right? We'll talk about that much later. In October, we'll actually talk about what that means. All right, everyone. Have a good weekend. Everybody sign in. I would expect a quiz. I would expect a quiz on Tuesday. I'll probably throw just a basic u substitution.